Why this matters. These examples aren't just exercises, they're tools for understanding the real world. Pilots use vector math to adjust flight paths for wind. Engineers use vectors to design stable structures. Boats, planes, and even spaceships rely on vectors to navigate tricky environments. By breaking problems into steps, visualizing the motion, and applying basic math, vectors become less intimidating and more powerful. Ready to dive deeper into vector subtraction, scaling, or products? Let's continue. Vector subtraction, finding the difference. Imagine paddling your kayak upstream. The river's current flows downstream, gently pushing you back. You're paddling forward, determined to make progress. As you fight the current, you can't help but wonder, how fast are you really moving? The water is slowing you down, but you're still gaining ground. To figure out your actual speed, we use vector subtraction. Vector subtraction is a way to measure what's left when two forces oppose each other. Think of it like balancing out two competing pushes. Let's break it down step by step, making it as simple as possible. Concept of vector subtraction. Subtracting vectors may sound complicated, but it's really about reversing the direction of one vector and then adding them together. Here's how. 1. Start with two forces or motions, vectors. 2. Flip the direction of the vector you want to subtract. 3. Add the two vectors together. Let's see this process in action with a few examples. Example 1. Relative velocity of two boats. You're in boat A moving 3 miles per hour upstream, and boat B is moving 2 miles per hour upstream. What's your actual speed relative to boat B? Step 1. Represent the velocities as vectors. Boat A's velocity upstream, A equals positive 3 miles per hour. Positive direction is upstream. Boat B's velocity downstream, B equals negative 2 miles per hour. Negative direction is downstream. Here both boats are moving in opposite directions, so their velocities have opposite signs. Step 2. Flip the direction of boat B's vector. To subtract B, we reverse its direction. Negative B equals positive 2 miles per hour. Step 3. Add the vectors. Now combine boat A's velocity with the reverse boat B's velocity. R equals A plus negative B, which equals 3 plus 2, resulting in 5 miles per hour. Step 4. Interpret the result. The result R equals 5 miles per hour means you're moving 5 miles per hour upstream relative to boat B. Why it's helpful. This example demonstrates how vector subtraction is used to determine the relative velocity between two objects moving in opposite directions. By flipping the direction of boat B's velocity, we accurately calculate how fast boat A is moving relative to boat B. Example 2. Walking against the wind. Intermediate. Now let's look at walking into the wind. You're walking 5 miles per hour east, but the wind blows 3 miles per hour west. What's the wind speed relative to you? Step 1. Represent the forces as vectors. Your walking speed east, A equals 5 miles per hour. The wind speed west, B equals negative 3 miles per hour. Here positive means east, so the wind gets a negative sign because it blows west. Step 2. Flip the direction of the walking vector. To determine the wind speed relative to you, we need to subtract your walking velocity from the wind's velocity. This involves flipping the direction of your walking vector. Negative A equals negative 5 miles per hour. Step 3. Add the vectors. Combine your flip speed with the wind speed. R equals negative 3 plus negative 5, which equals to negative 8 miles per hour. Step 4. Interpret the result. The result R equals negative 8 miles per hour. The negative sign indicates the direction is west. Therefore, the wind is effectively moving 8 miles per hour west relative to you. Why it's helpful. This example effectively illustrates how vector subtraction works through the flipping method. By flipping your walking vector and adding it to the wind's vector, we accurately determine the relative speed and direction of the wind as experienced by you. Example 3. Rocket launch against another rocket. Advanced. Imagine rocket A is launching straight up with a thrust of 500 meters per second, while rocket B is descending straight down with a velocity of 200 meters per second. What's rocket A's actual velocity relative to rocket B? Step 1. Represent the forces as vectors. Rocket A's velocity upward, A equals 500 meters per second. Rocket B's velocity downward, B equals negative 200 meters per second. Here, positive means upward and negative means downward direction. Step 2. Flip the direction of rocket B's vector. To subtract B, reverse its direction. Negative B equals positive 200 meters per second. Step 3. Add the vectors. Now combine rocket A's velocity with the flip rocket B's velocity. R equals A plus negative B, which equals 500 plus 200, resulting in 700 meters per second. Step 4. Interpret the result. Rocket A is moving 700 meters per second upward relative to rocket B. Why it's helpful. This example effectively illustrates how vector subtraction is used to determine the relative velocity between two moving objects. By flipping rocket B's velocity vector, we accurately calculate rocket A's velocity relative to rocket B. Breaking it down, why subtraction matters. Reversing forces. Subtraction is just addition in disguise. Flip the direction of the vector you want to subtract, then add. Everyday uses. From paddling upstream to calculating rocket launches, vector subtraction helps explain the net result when two forces work against each other. Simplifies motion. Subtraction turns opposing movements into a single clear answer that's easy to understand. Next steps. Now that we've mastered subtraction, let's explore how vectors scale up with scalar multiplication or twist into new dimensions with the dot and cross products. Ready to dive deeper? Let's keep going.